Welcome.
Chapter 18 be posted right here? I don't think that they are.
Oh, okay. It looks like I did not update the actual course page with the link. Okay, do you mind going up to the top?
Yeah, sure.
Okay, thanks. Sure. I think I must have just posted the updated notes. So chapter 18. Oh, no? Okay. Looks like I didn't do either. All right. Well, my bad. Yep. Okay, thanks. Hi, thanks. Okay, so I'm going to get started. Today's announcements are the Chapter 17 sapling is now open, and it's due Monday, 9 a.m., since we finished Chapter 17 just last lecture. Exam regrades are due noon today, either in person or to my mailbox. So I have one exam here for pickup for someone who arranged that with me and their TA. If that's you, come get it after lecture. But yeah, if you have any more regrades to submit, I can take them here right after lecture, or you can drop them off at my mailbox. And then finally, the Chapter 18 notes. Someone just pointed out that I did not actually update the link on the website, but I've got the updated Chapter 18 notes finalized, so I'll post them as soon as I get back to my office later today. Okay. So questions about any of those? Okay, cool. All right, so last lecture we finished up Chapter 17, which was all about allylic and benzylic reactivity. Chapter 18 is similar but very different, as it turns out. So similar in some ways, at least. So Chapter 18 is all about vinyl and aryl reactivity. Okay, so I guess to sort of tie this back into what we were looking at just last time, Chapter 17 was about positions one away from a double bond or from a ring. So Chapter 17, we're looking at stuff like this, so like benzyl iodide or allyl iodide. And the common theme we saw there was that pretty much any reaction you want to do at those locations is going to be a lot faster than it would be without that ring or that double bond. So this is all really good at SN1, SN2, and E1. E2, it actually works better if the halogen is one atom further away, because we saw that the deprotonation is what needs to happen at the benzylic position there. Okay, so that's kind of summing up Chapter 17, is basically any reaction we've done in the past, way easier if it's at the allylic or benzylic position. What we're going to be looking at here is carbons that are right on the aromatic ring or double bond. So here we're looking at a halogen directly attached to an aromatic ring, or a halogen directly attached to an alkene. So these are, this particular one is phenyl iodide, which is a subset of aryl iodides. And this one is vinyl iodide. Okay, so it looks pretty similar at first glance, but it turns out there's a huge amount of difference between how these things react. These are really terrible at the regular alkyl halide reactions, really bad at SN1, SN2, and E1. They can be okay at E2 under the right circumstances. Okay, so that's kind of the general roadmap of the first part of this chapter, at least. Towards the end, we're going to look at some new reactions that don't follow any of these basic 4 alkyl halide reactions, that are things that are specifically designed for phenyl iodides or aryl iodides that we couldn't do before. Okay, so the first part of this is just running down the main 4 reactions and seeing like exactly why things get messed up on these molecules. So we're going to start with SN2. Okay, so SN2 on aryl vinyl halides is basically considered no reaction. So if you tried doing a setup like this for SN2, even if you've got a really strong base, good nucleophile like NaOET and HOET, nothing's going to happen. Okay, so there's several reasons for this. Some of them apply to both aryl and vinyl, some are just to aryl specifically. So the first one that's sort of more generally applicable is it has to do with hybridization of the atom that's getting SN2 happening on it. So we already know that the hybridization of the central atom is going to drop by 1 during the transition state. And we actually saw that pop up a little bit last chapter, but just as a quick refresher here, here's what SN2 should normally look like. So here's our leaving group, here's our carbon, here's our nucleophile, and normally carbon sitting around here in this state is sp3, but during the transition state, like we saw last chapter and also a bunch before that, hopefully, the carbon is briefly going sp2 hybridized, and then it ends up back at sp3 in the final product. So if we want to do an equivalent thing onto, say, our vinyl or aryl halide, instead of going sp3 to sp2, we're already starting out at sp2, so we're going to have to go sp2 to sp. So that might look like so our nucleophile comes in, kicks out our leaving group, and briefly we're going to something that looks like this, where the leaving group and the nucleophile are partially bonded on there, and the central carbon is going from sp2 to sp briefly. Okay, so we haven't explicitly looked at like relative energies of hybridization levels on atoms, but it turns out going sp3 to sp2 is actually quite a bit easier than going sp2 to sp energy-wise. So it turns out the energy cost, depending on circumstances, is going to be about 5 kcals per mole more. Than going sp3 to sp2. Which means that at room temperature, it's slower by about 4 orders of magnitude. So it's about 10,000 times slower. Even though it's exactly the same arrow pushing, it's got quite a bit more of an energy hurdle to get over by doing this. Okay, so I'm not sure exactly where that additional cost is coming from, if it's just poorer bonding to the leaving group or exactly what's going on, but it does turn out to be quite a bit trickier to go to an sp2 hybridized carbon than to, to an sp hybridized rather than to an sp2. Okay. So questions about that part? Okay, cool. So not only do we have to deal with additional energy costs from hybridization changing, we also have to deal with geometric issues as well, which we already know is a big deal for sp2, even in the best of circumstances. So geometric or steric issues. So again, I'm going to draw this vinyl halide sp2 thing, SN2 thing going on here. All right, so we know that if we want to do SN2 on that carbon, we've got to do a backside attack, which involves coming in pretty much in the plane of the molecule, as it turns out. So we're coming in the same plane as the other 3 groups that are already attached to that carbon. Unlike when we did it on this molecule up here, and I'm actually going to draw in some chirality stuff on here just to make it explicit that when we did backside attack on an sp3 hybridized carbon, we're actually coming in from like the middle of this kind of umbrella shape of the 3 H's pointing vaguely towards us. But we're not trying to squeeze in between multiple groups that are all in the same plane as where we're coming in from. Here, though, we're coming in from the same plane as both the CH2, or whatever the other end of that double bond is, and also the H. And so for CH2, it might not be quite so bad, but, sorry, let me add some details here. Especially once we have a substituted alkene, like if we start having extra R groups on the end of that double bond, now we're starting to get some serious steric issues where the nucleophile just straight up can't approach from the right angle because there's just not enough space to work around the R groups. So especially on substituted alkenes, the sterics kind of blocks backside attack. So not only is it like hugely grueling for the molecule to go through the process in the first place, but it has a hard time for the nucleophile even to get things started geometrically. Okay. If it's just a CH2 at the other end of this double bond, it turns out not to be such a big deal, but once you start bringing in R groups, it really slows things down. Okay.
So why wouldn't it attack from the top or the bottom as opposed to side like that?
Oh, so like coming in from here or here?
Yeah.
So it turns out that when you do SN2, it's got to be coming from the exact opposite angle of where the leaving group's doing it, or leaving group's pointing. Yeah, so it, I'm not sure which lecturers cover this, but if you sort of show the anti-bonding orbital, like if you're looking at the lowest unoccupied molecular orbital on this, it's sort of pointing out the opposite direction from where the leaving group is. So, okay. So other questions about this? Okay, cool. So that's geometric issues if we're attacking vinyl molecules. If we're doing aryls, it's got even worse problems because here's our ring with the leaving group sticking out. Our nucleophile is being asked to come in and do backside attack by attacking from inside the ring. And then after that happens, we know that the nucleophile is going to be pointing the opposite direction from where the leaving group was. So that's how that would look. Obviously that's not feasible. So this is just straight up impossible for aryl halides. For vinyl, so I showed as no reaction here. Vinyl, it is just extremely disfavored. It's just considered no reaction on any useful or meaningful time scale. But if you leave it to sit long enough, you will eventually get some vinyl reaction. But aryl is just straight up impossible, no matter how long you wait. Okay, so questions about that one? Okay, cool. So that's SN2. Okay, so E2 is kind of the odd one out of these four reactions. It's slightly different on the stuff we saw in last chapter, and it's going to be slightly different in this chapter as well. So E2 on aryl and vinyl halides. So in fact, we actually saw this happening already in chapter 14. Because if you remember the way that we made alkynes, actually I'm just going to say R there. So if you remember, when we wanted to make an alkyne from, say, an alkyl halide of some kind, we can take this, we can do strong base and get one E2 reaction to happen. And then if we react with another equivalent of strong base, we can do another, in the notes I said E2 with quotes around it. So it's not exactly the same as E2 was on a regular alkyl halide, but it's pretty similar. Okay, so if you look at it, this second step here, we're taking a vinyl halide, like a carbon-carbon double bond with a halogen on it, and doing an E2 elimination to get there. Okay, so we've already sort of used this a little bit for synthesis, but we haven't dug into the details on how it differs from like regular E2. So the difference between E2 on regular alkyl versus vinyl halides is that on vinyl, it doesn't have to be antiplanar anymore. So it can be antiplanar, just like it was when we were doing it for the regular alkyl halide. Or synplanar, which means that the Br and the H are actually pointing the same direction in the same plane. So antiplanar looks like that. Synplanar looks like this. Okay, so the reason for this is that before, when we were doing this on alkyl halides, like really all the orbitals care about is that the 4 atoms that are involved, the halogen, carbon, carbon, H, all have to be in the same plane. So really E2 doesn't care too much about either one of these. Like in theory, either one of them should work for alkyl halides as well. The difference is for alkyl halides, I guess to phrase this, synplanar in alkyl halides would work okay for E2. So like Br here, H here, and then whatever else out here. The problem is that this is an eclipse geometry, and so the molecule, since it's all single bonded, can just rotate out of that. So the molecule is never going to get lined up properly in synplanar for long enough for E2 to happen here. So even though E2 would happen, it's just not really a viable option. Like antiplanar ends up being the way that E2 happens almost all the time. Okay, so it really comes down to once it's in a vinyl halide, then it's pretty much locked in either way, and so E2 can happen whether it's locked syn or anti, because it's all going to be in the same plane then. Okay, questions about that? Okay, so the one downside is, I guess another difference between E2 on vinyl versus alkyl is that just like we saw for SN2, going to sp carbon still costs a lot of energy. So the second E2 reaction is still going to be harder. And slower, in other words. So going sp3 to sp2 here is pretty easy, but then the last step where you go to sp is quite a bit more difficult. So usually it'll do the first elimination and then sit there for a long time, and eventually if you keep forcing it, it'll go to the alkyne. And you can sort of make that happen in a few ways. One is just by sort of using a very strong base, so like sodium amide, NaNH2. That's actually why we traditionally use that base, because it's strong enough to force E2 to happen in a reasonable time frame. So that'll help it go, and also heating it up a lot helps. Okay, so questions about that? Okay, cool. So you might be wondering, okay, I've done E2 on vinyl halides, but I said at this heading E2 on aryl halides. What's going on there? The answer is it's complicated and Loudon doesn't actually cover this one. It turns out you can very, very briefly do E2 on an aryl halide as well, but it doesn't stick around for long for obvious reasons. 24, okay. So if we could get that as like a final product, that would look like so we're doing an elimination here. Yikes. Okay, so that should look pretty uncomfortable to you. Turns out this can actually exist very briefly on its way to something else. So benzyne, which is what this intermediate is called, not a stable product, but there is some evidence, or quite a lot of evidence, to suggest that it does exist briefly during some other mechanisms that we're not going to cover. Okay. So, and you'll notice this is actually violating our rule about minimum ring size for a cycloalkyne, which is another reason it's not going to hang around for very long. Okay, so questions about that one? Uh-huh.
So this couldn't be used in the synthesis?
No, it's very limited circumstances that you can make it under, and it pretty much immediately like reacts with whatever's handy. Yeah. So, okay. Oh, hi. Yeah. So good question. Yeah, a lot of the time trapping really reactive intermediates at low temperatures is something that people have done. I don't know if they've actually managed to do it for benzyne or not. I think like mostly it ends up being like a sort of forensic kind of thing where they're like, okay, we got these products out of it, and like if we label one of the carbon atoms with an isotope, maybe we can figure out that it like did this briefly and then went like somewhere from there based on where stuff adds. But yeah, I don't know if anyone's actually gotten a look at benzyne itself as is. So, good question though. Okay. So we've done SN2, we've done E2. Let's move on to SN1E1. And I'm going to do these together. Okay, so SN1 and E1 on aryl vinyl halides. This turns out not to work great either. And this really comes down to carbocation stability. Or instability might be a better way to put it. Okay, so remember that for both of these mechanisms, reaction starts with the leaving group dropping off, and then we get a carbocation, and then from there you can either do SN1 or E1. So that's why we're covering these two reactions together. By the time we actually get to the point where we have to pick between them, we've already sort of passed the bottleneck for the reaction, which is making the carbocation. So let's look at how carbocation formation works on aryl and vinyl halides and why it's bad. Okay, so for starters, we're having the same problem that we had to deal with for SN2 and E2, which is hybridization cost is a lot higher. So so not only are there hybridization costs, There's also no resonance stabilization available. Like there would be for the stuff from last chapter, say allylic and benzylic stuff. So if we show this thing here, with its leaving group dropping off, okay, so not only are we going sp2 to sp, which already kind of sucks, but if we show the shape of the orbitals on this thing, so I'm going to draw it sort of out in perspective here. Okay, so I'm going to do the pi bond here between the two carbons as like vertical p bonds on both atoms. So that's kind of where the pi bond is coming in. But then the other p orbital, the empty p orbital on this carbon, based on the orbital geometry, we know is going to have to stick out perpendicular to that. So there's like no orbital stabilization possible between this and the pi bond. There's no resonance that can stabilize it. Okay. All right, so I guess that's kind of two factors that are working against vinyl carbocation formation. Questions about those ones? Okay, cool. And then for aryl, we again have even more issues to deal with. So we're also trying to fit an sp carbon into a 6-membered ring, which we already know from up here and also from before is difficult. So if we have a leaving group drop off of here, then we're trying to go linear at this carbon, which is sp hybridized. And we were actually trying to do the same thing in benzene up here, which is, I probably should have drawn it more distorted looking. So there's going to be like some unhappiness in geometry on this molecule, like some combination of ring strain and trying to hold the carbon at a bond angle that doesn't agree with its hybridization here. But this is also not good. Okay, so for those reasons, like both of these have a very difficult carbocation formation process, and carbocations themselves are already, high enough energy as it is that anything we can do to destabilize the carbocation is going to really inhibit E1 and SN1. Okay, so questions about this? All right, cool. Oh, actually, sorry. One thing that I do actually have in the notes here is how this actually works out instead. Instead of going linear, the carbocation actually stays kind of sp2-ish geometry, even though it really doesn't want to. So it is actually going to stay more or less hexagonal. And instead of having an empty like regular p orbital, it's almost like an empty hybrid orbital. It's really kind of somewhere in between where there's like some fractional hybridization going on. I don't know exactly how much. So it's an empty sp2 kind of like orbital on an sp2 carbon instead of empty p. Okay, so obviously that's weird and unusual looking, and I guess if you look at it in terms of like s character versus p character of this orbital, usually we want to have the empty orbital have as much p character as possible, which is why we normally just do it in a straight up empty p orbital, just because those orbitals are further out from the nucleus and having a positive charge there is actually the least bad spot for it. Doing it in a hybrid orbital like this is kind of really bad for, I guess, electrostatic interactions on the molecule. But it's required by the way the geometry works out, unfortunately. Okay, so to top it all off, there's one additional factor on all of these. One more reason why SN1 and E1 are not great. And that is just getting the leaving group off in the first place is more difficult. Really, this actually applies to all of these reactions, so like SN1, SN2, E1, and E2. And that is that the carbon leaving group bond is stronger than it would be on a regular alkyl halide. Because if you remember from way back in like chapter 1, I think, having an sp2 carbon here means that its bonds, because this is an sp2 hybrid orbital, it's got a little bit more s character than the bonds coming off of an sp3 carbon. So sp2, all of its bonds have more s character, so they're shorter and stronger. Whereas here, they have less s characters, so they're slightly longer and weaker. Okay, so not only does the rest of the reaction have more problems, depending on which reaction it is, but also just getting the leaving group off in the first place is a little trickier too. Okay. So, questions about any of those big four reactions? Okay, cool. So, what can we actually do with these halides that are kind of useless for a lot of the chemistry we're used to doing on them? What we can do instead is some new reactions that we're going to start introducing. Okay, so the first one we're going to see in this chapter is similar in some ways to electrophilic aromatic substitution, but also the opposite of it in some ways. So instead of electrophilic aromatic substitution, we're going to look at nucleophilic aromatic substitution. If things were nice and tidy, then we would call this NAS to sort of match up with how we called electrophilic aromatic substitution EAS. Sadly, things didn't work out that way, and it's named more analogously to like how SN1 and SN2 were named. So this is actually going to be called SN AR. So just like SN1 was substitution nucleophilic first order, this is substitution nucleophilic aromatic. Okay, so SNAR for short. Okay, so let's kind of look at like the big picture of comparing this to EAS. So when we were doing electrophilic aromatic substitution, what we did was get an electrophile somehow, so either make it or just add it as is. Then we're going to have the ring attack it and put a positive charge on ring. Then whatever we've got on the ring already, if anything, needs to stabilize the positive charge. So electron donating groups stabilize the positive charge. And electron withdrawing groups destabilize it. Actually, I'm going to wrap around because there's one more part that I need to add here. Okay, and then once we're done with that intermediate, the way that we finish the reaction up is we pulled a proton off of the ring. Okay, so pretty much everything in electrophilic aromatic substitution is dealing with a positive charge comes in from somewhere, we have to manage that positive charge during the reaction, and then we kick it off with a proton at the end. Okay, so nucleophilic aromatic substitution is the exact opposite of that. So we're going to have to either make or add a nucleophile. So we're dealing with negative charges this whole time. So rather than the ring attacking like it did up here, we're having the nucleophile attack the ring. So the ring now gets a negative charge. So everything that we learned from before about electron donating groups are activating and electron withdrawing groups are deactivating, now it's flipped. So electron donating groups destabilize the negative charge because we don't want to shove any more electron density into the ring. It's got too much already. Electron withdrawing groups stabilize it. So all of our activating and deactivating stuff is flipped. And then to finish things up at the end, we need to get that negative charge out of the ring. We can't kick out an H- because that's pretty high energy and unstable, but we're going to kick out a leaving group with a negative charge to finish the reaction. Okay, so pretty much all the differences between the two reactions comes down to, do you have a plus or a minus charge? Okay, so let's take a look at how that would happen. All right, so another consequence, I guess, that well, here, let's sort of work through one example and then talk about why things are the way they are. Okay, so I'm going to do this reaction on this molecule here. I'm going to use methoxide as my nucleophile. So rather than having the ring go and attack something like I did during EAS, I'm going to have this go and attack onto here. Now this carbon of the ring has too much electrons to obey the octet rule, so it's going to have one of its pi bonds break onto there. Okay, and note that we're breaking aromaticity by doing this, just like we did in EAS, only now it's because we have too many electrons instead of too few. But we do still have one carbon in the ring that has 4 total bonds to it, and so this is the one where we're going to have to pull something off at the ends to make things work. Okay, so we can show this minus charge moving around the ring. And if you remember, we're still looking for those 3-atom groups when we're showing resonance. It's just the arrow pushing is going to look different. So we can put it there. Or, actually, let me scoot this out a bit. Okay, so we know that when we had a positive charge on the ring during electrophilic aromatic substitution, being right next door to a nitro group like this was a huge no-no because having plus next to plus was very destabilizing. Here, we're having minus next to the plus of the nitrogen, so things are actually way better than they would be because of the nitro group. And we actually have access to one additional resonance form where we kick that minus charge out into the nitrogen and break up the double bond O. So we can show nitrogen with 2 O minuses on it. Going to that. So it's kind of analogous to what we did a couple chapters back, where if we can boot the charge out of the ring entirely onto a substituent group, things are going to be way easier for the reaction overall. And then there's a 4th form that I'm not going to draw out, but we could look for another 3-atom grouping and get the minus charge over to here as well. Okay. So this set of intermediate states actually has a specific name. This is called a Meisenheimer complex. And it actually turns out to be frequently very brightly colored. Just because of the way the relative orbital energies work out and the way it interacts with light. I think those of you taking lab will see a little bit more of like color versus electron density stuff like a few labs from now. Okay, so then to finish up the reaction, you just got to kick out the leaving group, which is the fluorine in this case, and reestablish aromaticity. So whichever resonance form you're showing doesn't really matter. You can do this from any of them. It's just simpler looking from some than from others. Okay, so let's do it from this one. So we can just kick down here and boot out the fluorine leaving group. And that gets us our aromaticity back. And we've swapped out our halogen for a new, what came in as a nucleophile. But we didn't do it by SN1 or SN2. We did it by this new SNAR reaction. Okay. So questions about that? Yeah? So generally the same ones that we saw for SN1 and SN2, but they've got to be sort of on the stronger end because making a C with a minus charge is kind of a big ask for the molecule stability-wise. And so usually like any strong nucleophiles, strong base, good nucleophiles will be okay doing this. There's also limitations based on what else is on the ring, but we can cover that next time. So, Okay, so I'm going to wrap it up there, and then we can pick this up on Friday.